So now that we have looked at an interacting system, how to handle such an interacting system in weak limit of interaction, weak interaction limit, we want to see how really it does compare with real life examples. Of particular interest is the phenomenological equation of state, which is p plus n square a over v square, v minus n times b is going to be nkbt. If you have not encountered such an equation, this is for a hydrostatic system, which should be clear to you now because your thermodynamic variables are P, V and N, and this is called van der Waals gas. But how does one arrive such an equation? So what we want to start off with the interaction. So once again, the starting point is the pairwise interaction. And here, of course, we say that there is a definite size sigma, below which there is a hardcore repulsion, but there is a soft attractive part to this, so that V of R is minus epsilon sigma over R to the power 6 for R greater than equal to sigma. Something like this. The Hamiltonian then is p square sum over I p square pi square over twice m plus sum over I u of I, where ui is the potential energy of the ith particle. So one can write down u of I as sum over I less than j. There is a sum over j v of rij. Now one can take care of double counting. Well, we will see. So I can bring in a factor of half here, and the reason of bringing the factor half is going to be very clear. So but for the time being, let's write down this explicitly and write this down as sum over ij, I less than j, v of rij. So this part is the potential energy, total potential energy, and we will describe it as sum over individual particles. But now this interaction is pairwise, so I bring in a factor half. What I want to do now no, restart. The Hamiltonian of the system is given by sum over I pi square over twice m plus sum over I comma j with I less than j v of rij. Now here, this is one way of writing it down, but you have, with the fact that you are taking into consideration that I must be less than j, and this restriction itself essentially ensures that there is no double counting of pairwise interaction. But no harm in double counting. For example, I can consider v of r12 and v of r21. That is perfectly fine. Only thing I have to ensure that if I get this restriction out of the picture, which we will do because of our interest in treating the problem in a kind of a mean field approach, we will write half V of Rij, where there is an unrestricted sum over I and j, and essentially then this becomes pi square over twice m plus half sum over I u of I, where I is the small u of I is the interaction energy of the ith particle. This term u is sum over half sum over I, u of I is the total internal energy of the system. The first term is the total kinetic energy of the system. Now the idea is we want to look at it in a mean field way, not a weakly interacting system, a dilute system I have. So I have the ith particle, and surrounding this particle, let's say I consider a radius of r. So if I have a radius of r, this is a poor radius. Maybe one needs to draw a circle first, and at the center of this I have the ith particle, and there are particles inside this with which this ith particle is interacting. How many particles can it have? Rho times the volume, right? Pi 4 by 3 pi r cube. So the idea is that I want to replace this u of I by a mean field energy that this ith particle feels, and the way to do that is we can write down this phi, or let's say we will just write ui. Now this is a function of r, but now I am going to make it independent of r, and I am going to say, oh, I have the density of the particle is rho, therefore the total number of particles that is contained in this volume is between 4 pi r square times rho dr, and each of the pairwise interaction that you take is of the form ui. We had v of r, so this is going to be v of r, but the limits of integration are from sigma to infinity, because that's where the potential, how the potential behaves. So this becomes minus epsilon 4 pi sigma, there's a rho, there's a sigma to infinity, r square v of r dr, which is minus 4 pi epsilon rho sigma to the power 6 sigma to infinity r square 1 over r to the power 6 dr. That gives you minus 4 pi epsilon rho one over r to the power 4 dr sigma to the infinity r to the power minus 4. That is a very trivial integral, 4 pi epsilon rho r to the power minus 3 divided by minus 3 sigma to infinity, and when you put in the limits you will see that this is going to give you minus 4 by pi 3 epsilon rho, I missed a sigma 6 factor, sigma 6 over sigma cube, which is minus 4 by pi 3 pi epsilon rho sigma cube. Please note that this description is only valid when it's a weakly interacting gas, where the density is very dilute, you are at high temperatures, so that the particles rarely see each other. So essentially what you do is, look, you kind of average out the interaction energy surrounding the particle. So if a particle separation is r, how many particles, if you consider this, how many particles are contained over here, and then you integrate out the whole volume, and essentially you come up with this expression, which is no longer dependent on the position, so that the total energy is now half sum over ui, which is half, we will not n times this number minus 4 by 3 pi epsilon rho is density is n by v sigma cube. Now you clearly see that this quantity is minus A times n square over V. This is your potential energy. So the Hamiltonian, which you started off with the many particle Hamiltonian, now simplifies to pi square over twice m. Now here I am going to change the level by saying that I goes from 1 to 3n, remove the vector sign on the momentum, and the energy is n square over v, and this must be equal to E. So if you are considering this system to be isolated, then essentially you are looking at the microcanonical formalism of this. So this becomes I equal to 1 to 3n pi square over twice m is going to be E plus a n square over v. So this is the surface that you are considering. What is the total number of microstates? But before you calculate the total number of microstates, you must realize that I also have to figure out the volume accessible to these particles. If they are point particles, no size, then of course each of these particles can have a volume V, and therefore the total number of microstates, if I write down omega V, omega r, the coordinate space and the momentum space, omega r in the ideal gas case was V to the power n, because they are not interacting, therefore they could have been taken as point particles, and each of these were allowed to take the volume V. But now in our case, they have a finite size, they have an interaction. So clearly you see that the total, if sigma is the particle size, total number, the volume that is accessible to each of them is going to be this raised to the power n, because this is the volume that is accessible to a single particle. Omega p is the volume contained within the hypersurface that is defined by this relation, and we have calculated that was pi to the power 3n by 2 gamma 3n by 2 plus 1 r to the power 3n, right? Yeah, by 2, where r square is twice m E plus a n square over v. Hence, the total number of microstates that is accessible to the system is omega evn is going to be v minus n times sigma raised to the power n 1 over n factorial h to the power 3n. That's the standard indistinguishability criteria, and that's non-dimensionalizing the total number of microstates, the ad hoc introduction of this factor. And then I have this result, which is pi to the power 3n by 2 gamma of 3n by 2 plus 1 twice m e plus a n square over v raised to the power 3n by 2. Our job is almost done. I know the total number of microstates, and the rest of the thermodynamic quantities I can easily calculate. We start off with the entropy, which is Kb ln of omega. The entropy now I can write down as Kb n ln v minus n sigma plus this pi to the power 3n by 2 I can include. First let's simplify things, and then we will expand the log. We will write it as ln of 1 over n factorial v minus n sigma raised to the power n, and then I see that the denominator is h square raised to the power 3n by 2 pi to the power 3n by 2 3n by 2 factorial gamma 3n by 2 plus 1 is 3n by 2 factorial. I have twice me plus a n square over v raised to the power 3n by 2. So that I write this as kb ln 1 over n factorial v minus n sigma raised to the power n twice m pi over h square times e plus a n square v raised to the power 3n by 2, and then I have 3n by 2 factorial. Now let's take the log. So that this gives me kb n ln v minus n sigma plus ln twice m pi over h square e plus a n square over v raised to the power 3n by 2 gives me 3n by 2, and then I have minus 3n by 2 ln of 3n by 2, I have plus 3n by 2 that comes from this. I have also an ln n factorial which is going to give me n ln n plus n. Let's take an n outside, gives me nkb ln v minus n sigma plus 3 by 2 ln twice m pi over h square e plus a n square over v. Then I have minus 3 by 2 ln 3 by 2n plus, sorry, there is also going to be a minus ln of n plus 5 by 2. So the entropy now, I can simplify this as 5 by 2 plus, what else can I do? Let's see. I can take this part, write down this as minus 3 by 2 ln 3 by 2 minus 3 by 2 ln of n minus ln of n. So that this gives me minus 5 by 2 ln of n, and I have this term is going to be ln 3 by 2 raised to the power 3 by 2, right? So this is just a constant term which is not very interesting to me, but anyway, we will keep the 3 by 2 here, minus ln 3 by 2, so that I can combine it over here. This is going to be v minus n sigma plus 3 by 2 ln twice m pi over h square e plus a n square over v, and then these two terms. Please be careful with this. This is going to be minus 3 by 2 plus 3 by 2 ln minus ln. Is this correct? No, sorry, this is minus. Correct, minus 5 by 2. 5 by 2 ln of v minus n sigma. See, all these details, minute details, are not very necessary because after all you're going to take a derivative with v and e, but nevertheless ln twice m pi over h square. Now you have a 3 by 2 minus 3 by 2 ln 3 by 2. 3 by 2 is common, so essentially you are going to have times 2 by 3 e plus a n square over v minus 5 by 2 ln of n, and this is the answer that you're looking for. So we will finally write down this as 5 by 2 plus ln v minus n sigma plus 3 by 2 ln of 4 by 3 m pi h square times e plus a n square over v minus 5 by 2 ln n. Remarkably, it has a very similar structure as for the ideal gas. The difference comes in here and here. You have the residual part that is remnant of the ideal gas, which is this term and this term. Del S del E is going to be 1 over T, right? N and V held constant. So that means if I take a derivative of E, I have 3 by 2, 4 by 3 m pi over 8 square E plus a n square over V times 4 by 3 m pi over 8 square is going to be 1 by T. So that I missed out the NKB which is sitting outside, so I am going to have an NKB. So that 3 by 2 NKBT is E plus a n square over V, right? What about the equation of state, that is del S del V, E and N held constant? So this, by the way, you should note that this is the desired fundamental relation of type 1, which we have already been, which is kind of the holy grail in thermodynamics, right? So when once I have P by T is equal to del S del V, E and N held constant, let's calculate that derivative. The volume only appears over here, also here. That one has to be very, very careful. So I have NKB. The first term is going to be V minus N sigma 1 plus 3 by 2. I'm going to have E plus a n square over V 1 over this, and then I'm going to have del V of E plus a n square over V. So that I have NKB 1 over V minus N sigma plus 3 by 2 1 over E plus a n square divided by V, and this derivative gives me minus a n square over V square. NKB 1 over V minus N sigma plus 3 by 2. Let's use this relation. This is 3 by 2 NKBT, right? Minus a n square over V square, P by T. There are cancellations. 3 by 2 cancels out, and I write pressure as NKBT 1 over V minus NB plus 1 over NKBT minus a n square over V square, and close the bracket. This NKBT, I can take it inside over here and then over here, and you see that this is going to cancel with this, so that I'm going to be left out with NKBT divided by V minus N times B minus a n square over V square, so that the equation of state becomes a n square over V square times V minus N sigma, sorry, not B, this is going to be sigma, N sigma is going to be NKBT. So you nicely come up with the van der Waals equation of state, right? It's a purely phenomenological equation of state and can be derived within the mean field approach by saying that you are looking at a very dilute system of a gas, and you kind of replace the interaction energy by a mean field energy, which you obtain by picking up the ith particle and looking at the contribution of all the jth particles surrounding it. That's all. Good. Now I have P plus a This is the question we want to ask. NKBT divided by V minus N sigma. So that I can write down this as NKBT over V 1 minus N by V sigma inverse. Now you clearly see, therefore, this quantity is going to be NKBT over V. I can expand for weak enough density, for very low density, so that this term is 1 plus N by V sigma plus N by V sigma square plus higher order terms. Therefore, pressure is AKBT over V plus NV whole square, if I open the bracket, KBT times sigma minus AN square over V square plus higher order terms, and then I again take NKBT common, which gives me 1 plus N by V sigma minus A plus higher order terms. So that your second virial coefficient, you see that this expansion clearly has rho 1 rho times B2 plus rho square times B3, so on and so forth. This is rho of KBT is equal to P. So even this phenomenological equation, which actually describes lots of gases, actually can be written down in the same form that we had arrived at when we looked at the interacting system. And clearly here, I think the B2, the second virial coefficient, is going to be sigma minus. Sorry, one has to be careful. If I have taken KBT outside, this has to be A over KBT. A has the dimension of this thing, right? Yeah. So this is your second virial coefficient. Alternatively, you can also absorb the KBT in the second virial coefficient and define B2 as KBT sigma minus A. A has the dimension of energy. Please remember that.